and loop or touch fastener where you've got the two different surfaces. And the manufacture of that material is pretty interesting as well. So if you're interested, have a look at that. US patent law, of course, is time of filing that's important, not time of invention. So here we have the very similar US patent filing from de Mestral filed in 52 and I think granted in 55, as the patent says. So look those up. They're always interesting. You find out a bunch of more information by looking through patents sometimes than you do from other literature. Back to our gecko again. How can it walk on the ceiling? And as an article that I remember about 12 years ago in New Scientist here, the important thing is that we don't have an adhesive or glue mechanism. The entire weight of the lizard can be supported by this, and it relates to the millions or billions of these nano hairs, 10 to 100 nanometers across at the bottom, called setae. Seta is the singular, S-E-T-A, and that S-E-T-A-E is the plural, so a multitude of these, and they bend and conform to the surface, and they maximize those van der Waals attractive forces. And here's that article. I had vague interest before 2003 in this on geckos, but around 2003 was when my interest really was piqued by articles like this and the work of Kellar, Autumn, and another professor we'll hear from in a minute called Kelly Miller. So one of the things that you can do is you can take your gecko and you can put it here on a gallium arsenide wafer, which is hydrophobic, and the gecko will still attract very nicely to that hydrophobic surface, that gallium arsenide wafer. So it tells you that it can't be capillary attraction. So moisture is not involved here in this. You can actually, and again, Kellar Autumn's work here, you can measure that adhesive force of a single gecko foot hair now with a variational and atomic force microscope. So you can actually measure in nanonewtons that attractive force. And when you multiply your nanonewtons up by billions, this is where you get the approximate 1 Newton attractive force of a whole gecko to the surface. As I said earlier, if all the feet push down simultaneously with all the pads, it would be about 10 newtons, and the gecko wouldn't be able to remove its foot from surfaces. So it has that strange unpeeling effect, or peeling effect, should I say, as the foot is removed from a surface. Application areas, well, yes, that's the important thing. This is from that revered organ, the Daily Mail, from England in February 2008. This is a bandage that mimics the gecko's ability to cling to surfaces, so that article there. And more interestingly, I think, a defense mechanism of little pads or gloves that would allow, in the defense industry, a soldier to climb vertical surfaces, and there's an illustration on there. If you do a little bit of search on DARPA and Z-Men, you'll probably come up with similar types things where the ability of a soldier with full pack to climb surfaces like this is shown. So we can very often take something from nature and work on it for other applications, be it a bandage, which I suppose is good, and we all think of defense as being vital, but maybe a bit more dangerous. There's a book called Gecko's Foot, actually, by Peter Forbes, and there's a single chapter in it, so it's a little bit deceptive because the whole book isn't about gecko's feet. It's about various aspects of nature's materials providing engineering experience there. So, but chapter 4 in that book, which you can probably now get as a fairly cheap or remaindered book from AB Books, it's got a whole bunch of interesting articles in there. couple of other useless facts, maybe, or interesting facts, if you're me on that. If you've got a dead gecko, it'll adhere just as strong as a live one to a ceiling. So some people have told me that they've come into rooms with lizards or geckos on which have been dead but still clinging to the ceiling. And the other interesting thing that Kellar Autumn did was he attempted to fool the gecko by putting a lot of dry polystyrene spheres on surfaces and getting those to attach to the feet. But it has this self-cleaning mechanism that comes from that roll-off that we saw earlier, that after 3 or 4 strides, the gecko is able to remove all of those polystyrene beads, or a huge quantity of them, and is able to continue its move across surfaces. So that's a couple of really interesting facts. Hans Rumpf, he is the founder of the German particle school, basically, in Clausthal in Germany. And a couple of pictures that I saw many years ago really did inspire me to see the forces of attraction. These are gold spheres on anthracene surfaces. So the anthracene is deformable, and they've been subject to a centrifuging process, and what that has done is deformed the surface and pulled the anthracene up to the gold particles. So we get these wonderful structures that we see here of spheres on tops of mountains caused by this attraction of particles to surfaces. So if you ever want to think whether these forces are significant or not, and these are particles of 10 microns or so, and below. So you're looking in that scale something that we don't intuitively think of as happening. But look at that wonderful left-hand picture of the almost Pluto-like landscape of things that we grasp to understand. Also visible on the macroscopic scale, of course. This was from the bedroom window of a house I rented in the UK many years ago before I departed, so you can actually see those 2 spheres attracting each other on bottom right. And where was this wonderful place I rented? Well, it was called Wilton Place in Dimmock in Gloucestershire. It looks an impressive building that was divided up as apartments, and I rented the one in the second arrow there, and those are the 2 spheres that you saw early. So 2 useless slides for you, but shows something that I can, nostalgia ain't what it used to be. I show in a number of talks that you have seen and a number of presentations, the white papers, etc. The slide on, or the picture on the left-hand side, and that was basically an adapted or morphed form of the full diagram that I show on the right, just to show that I've tidied up the diagram somewhat. We're showing the adhesive forces. You'll see on the vertical axis the ratio of the forces to the gravitational acceleration, because a lot of these experiments are done by having particles on surfaces, subjecting them to acceleration and seeing which particles remain, or deceleration. So you have particles on a mica or glass surface, you stop the descending glass or mica very quickly, and then you see which particles remain and which particles are detached from the surface. And you'll see there are other forces that cause attraction between particles, thermal force and whatever. The tidied up diagram, I think, is easier to understand. As we go down in size, that magnitude of attraction increases markedly, and that's from Norm Davis's book that he edited called Aerosol Science, that's got some wonderful chapters in there, including one on adhesion. So there's a copy of the book just shown on bottom right there, and some of those accelerations shown. So down at 100 nanometers or so, we're needing something between 10,000 to 100,000 times the acceleration due to gravity in order to detach a particle from a surface. And Hans did write this interesting book as well called The Bombing of Germany, which is, the reason I show it is more from the foreword or note from the publisher that was on the back, and the and the forward inside the book. They're identical. The book, the rear of the book, and the forward. But basically, a disclaimer of the book that claiming that Hans was only showing a biased view. So it's not often that you get a published book with a disclaimer from the publisher. Here he is, a jolly-looking fellow on the right here, and it's a translated book. They're called Particle Technology in the series that comes out from, I think now under Springer, but Chapman Hall in those days, and the same diagrams that you saw from Terry Allen's 4th and 5th editions, particle size measurement. But this is a good read and a good book, and well written. A couple of classic papers. I showed some pictures earlier from the ceramics processing before firing paper. That's the second bullet point there. And if you look at another paper called The Strength of Granules and Agglomerates from 1962, earlier than that 78 paper, you'll see some standard diagrams mapping out the range of forces from van der Waals to capillary to solid bridging. And then that last book that I've just shown, Particle Technology, Chapman and Hall from 1990, but it was translated from an original, an earlier German book. So here is that 62 paper that I talked about. Little bit complicated. You'll see the van der Waals forces at the bottom left there, holding particles together. There's the vertical axis being a theoretical tensile strength of the agglomerates. You'll see as we go up, the van der Waals forces are weak. The capillary forces are stronger, and in the towards the center there, and the solid bridging between particles that occurs from either crystallizing salts or from solid-solid diffusion is shown at the top right there. And you have to relate those forces, as I said earlier, to inertial forces or gravitational forces, and as we get smaller and smaller, those van der Waals forces, those attractive forces, become more important. So that's adapted. Another good book that I could recommend is Clyde Orr's book called Particulate Technology. Again, probably a cheap buy on ABE Books from '66. He's adapted the plot in this format where we see van der Waals, capillary, and adhesive bonding and solid bridging on top right there, and that theoretical tensile strength in kilograms per square centimeter. So where you look at different forces due to different mechanisms of adhesion, this is going back to the paper in 78 from Hans Rumpf in here. We show the different binding forces. You'll see EVs in here in relation to electrostatic forces, where you see those, and we'll see again the magnitude of those forces decreases as we, the magnitude of those forces increases as we go down in size, and at the bottom end we'll see those van der Waals. So this is the attraction of a 10 micron sphere to a flat surface. That's one of the most modeled types of interaction. We also have spherical interaction as well. So a couple of general points here. These VDW forces fall off pretty rapidly with distance, and at 1 micron or so separation between particles and surface, they're virtually absent. And then if we're considering liquid forces, we have to consider the radius of the sphere as well, and the distance between the particles. So there we have a critical distance where those forces become significant as the particles get closer, but again they're absent much beyond a micron or so. The only forces that remain beyond a micron or so are those electrostatic ones that's why I don't like the term electrostatic stabilization in wet and prefer charge stabilization, because I'm thinking electrostatic, I'm always thinking of rubbing balloons or cat's fur or winters where we get electric charges. The other forces that sometimes forgotten but become important in things like magnetite or iron are magnetic forces, and they can operate, as you'll know, from poles of magnets over quite significant distances. We've mentioned Kellar-Orton. We'll mention in a minute Kelly Miller from Colorado School of Mines, or at least that's when I first encountered the work. Two modern-day players, and anything you read from Jim Adair at Penn State is eminently readable and very well explained as well. And then the classic book by a name that I always find difficult to pronounce, Israel Achvili, the Intermolecular and Surface Forces. So if you're looking for a general textbook that covers all of these forms of intermolecular and surface forces, that's the classic and standard textbook. So there's a PhD student, Kelsey Eccleston, and Professor Kelly Miller at CSM, as it was. I think these experiments date back to maybe 2001 or whatever, and this is in effect a very simple atomic force microscope, but on the larger scale. Two micromanipulators, two borosilicate glass spheres of various types they looked at. They looked at slip and roll type mechanisms, but the simplest one is a straight pull that we'll see in a minute. Kelly Miller's video of this, or probably Kelsey's video if I'm more pedantic here, where the separated spheres are kept apart. They're then made to touch and then pulled apart. One is held stationary, the other is moved, and then you can see the distance. You can work out the forces at which separation occurs. So maybe the video is better to explain. So here we have the separated borosilicate spheres attached by epoxy to glass capillaries. And then what we do is we keep one stationary and we pull at the top the other sphere, and there's a point that's going to happen soon where those forces cause separation. I'll show that once more because it's a quick video. So here we have the separated spheres. They're made to touch. They're still holding together by van der Waals. We then pull up on from the top, and then there's a bending or flexing of the lower one. We can't see that here, but you can then allows you to calculate the forces. And if you do that, you see the attached forces, you see the pull-up, you see the detachment, and then you can do a little bit of simple math in order to work out what the force is needed, and you're looking at nearly 1,000 nanonewtons here, which would be a micronewton if that's an SI unit. It probably is. And then the simple attraction between pairs of particles here. A is the Hamaker constant here, and you can then work out, we'll see Hamaker in a minute, you can then work out the distance that those forces are operating over, and you can see it's about 2 angstroms or so, or 0.2 of a nanometer. So they're very close interacting forces, so a nice simple experiment, and I recommend looking up that literature. So we've got these forces operating over small distances, as you saw here, maybe 2 to 10 angstroms or so, 0.2 to 1 nanometer. They're very powerful, and in a dry system, they will ensure that you get irreversible, actually, aggregation dependent on size. And there's enough thermal energy in Brownian motion in the solid at 100 nanometers and below to cause interparticle diffusion. Well, again, that's coming up. So what you end up with a dry powder, this is electron micrograph, probably one of the first taken, or an early one. This is from an ASTM meeting in 1941. good paper, again, well worth looking up. This one, this paper in a range of particle sizing papers. This is called the electron microscope in the determination of particle size characteristics. And this was when electron microscopy was new. This is a titanium dioxide pigment there, and you'll see even though it seems to consist of separate particles, they're all fused together rather like an archipelago, maybe like the Philippines or like Japan. They're all fused particles. So transport-wise, they all act like one large particle. Surface area-wise, of course, most of that surface would be accessible to gas or to a catalyst or whatever, but this would block a 1 micron filter, even though the primary particle size could be seen as 300 nanometers and below, and it's that solid bridging that's occurred that causes many issues. So in terms of adhesion forces, we've got, as I mentioned, I think quite early on, that those inertial forces scale as mass, but the attractive forces relate to our available contact area, and our van der Waals forces scale as a sixth or seventh radius dependence there. So dispersion, separation of particles, this is a consequence, is going to be tougher as we go below 5 microns or so, and those forces, those van der Waals attractive forces, become strong in relation to inertial forces. Conversely, if we've got chunky material, and by chunky I mean larger than 20 or 30 microns, there's not any tendency to agglomerate there. There may be capillary attraction, but those particles will tend to be able to operate on their own as separate, discrete particles. With very small primary particle sizes that may be produced either in colloidal suspension or in atomized form, then as soon as we bring particles in contact with one another or with a surface, then we can end up with issues or problems of solid-solid diffusion. And all powders contain some degree of agglomeration. The smaller they are, the more agglomeration and aggregation is there. A couple of illustrations of that. The semiconductor industry, of course, in class 1, less than 1 particle of half a micron and above per cubic foot of air, then getting those submicron particles out of the system so they can't fall on wafers and produce defects becomes important. When you drive along in your car, that should say windshield actually, I don't know, this is a slide that I created many years ago when I was in the UK, so I didn't translate from English to American, so we have, should say car windshield there, not windscreen by the way, so I have to translate for viewers that only understand the second form. If you're driving along when the sun is low, probably at this time of fall season or in spring, very often you'll note that blue haze, the same sort of blue haze from a cigarette smoke that's uninhaled. You'll see that blue smoke attached particles to the windshield that you can only remove with a cloth and maybe with a surfactant there. That blue is caused by basically sub-micron particles attached to the inside of the windshield. Similarly, on the dirt on a shirt collar, we have the ways that we can remove or cause the particles detach with a surfactant or surface active agent. So that's another illustration of small particles on surfaces that adhere strongly. We look back at the history there to familiarize you or refamiliarize you with the van der Waals gas equation. That's the general form of it there, and what van der Waals did was he subtracted an amount from the volume of that classic PV equals RT gas equation, subtracted a volume to account for the actual size of the molecules, because there's zillions in gas, of course, and they occupy some real space, and added a term A over V squared to the pressure that accounted for those attractive intermolecular forces that kept particles together. Interestingly, you may remember Gustav Mie from his light scattering. Well, he wanted theories of everything, and in 1903 he was looking at the interaction between pairs of particles or particles and surfaces, and came up with that generic form with an r to the n in there, an r to the m equation. And then he was including a repulsive force as well. So if things have identical charge on them, or the same charge, should I say two positives or two negatives, they'll tend to repel. And that was developed by Leonard Jones. That's one person, by the way, not two people. So very often you'll hear people thinking that that's two people, but the Leonard Jones potential is that r to the 6 and r to the 12th dependent. So you sometimes hear that called the 6-12 rule. And then we have London forces as well. And be careful, it's not pronounced as English people would pronounce the city London. It's London. And he's got a general theory from Transactions of Faraday Society in 1937. And you'll see those similar A over R6 terms in there as well. The other main player in this, or the constant that comes in, is called a Hamaker constant, and this is a constant that deals with different materials. So in the old days, you'd get tables of these various constants, and it's used in equations where you've got that separation between surfaces or between particles and the radius of the sphere there. And the reason I highlight his 37 paper here is that if you go to it, you'll find there's an appendix in there, and he demonstrates by some simple math that the forces between two particles of the same composition must always be attractive. So unless, of course, you've got something else taking place, like electrostatic issues. So if you charge one particle negatively and the other positively, then of course you can have repulsion. But in the usual case, those van der Waals forces are always attractive. And then Hamaker looked at particle attraction. The Lifshitz van der Waals attraction looked at molecular attractive forces between solids. So this is a paper by Lifshitz from Soviet physics, I think one of the first papers that looked at that. So very often you'll hear that attractive force called in that terminology. Simple example from 1954, just to show this, and I've shown this these series of 3 slides or so before in when we looked at the USGS lunar simulant material maybe a few years back there, but just showing you how simple, and I'm working in CGS units there for those of you that don't understand dynes or ergs and all of those things, but it's very simple math here. That constant for quartz is shown to be 212 in the appropriate units there, and you can then work out where particles will attract. You can then do little equations, little spreadsheets, meter, micron, nanometer or so, and you can see that you can calculate then the accelerations needed to remove particles at, say, a micron or so, or 100 microns, or 10 nanometers. And you see at 10 nanometers, you're up to about 10 to the 11 G, and those numbers are higher than you got from that Davis plot I showed earlier, probably by 2 orders of magnitude, but don't worry about that too much. It's just that they are very significant. How were some of these experiments done practically as opposed to theoretical calculations? So if you've got other things in there like water between, then that causes additional attraction. But as I said earlier, you can attach particles or just put them onto, say, a plate, stop them very rapidly, calculate the deceleration, and see how many particles remain and how many are dislodged. And as I say, these values shown in Davis's book are about 2 orders of magnitude lower, but they're still substantial. So this is another important point is if you change the contact area in some way, and this is a distorted or aspheric sphere in here, you increase the contact area between particles also. So surface roughness obviously plays a very big role. Spheres are specific or mathematical concept, but if you increase the area, then you get different adhesive forces occurring, and this gives you a guide to how you can prevent some of that particle-particle attraction, and that's by having smaller particles in between the larger particles. So flow additives tend to do this type of thing. They're much smaller particles like fumed silica or maybe carbon black that are put into a system, and they allow those larger particles to roll over one another without coming in contact. So in effect, it's a steric separation of those larger particles. So if you put those finer particles, fumed silica, as I say, is a very good illustration of this. The aerosol type of products, Aerosol 200 from Degussa, one of those, no advertisement there, but it's a material I worked with a lot in my PhD. But those materials allow the dissipation of those attractive forces, and they're acting a little bit like bumps on the surface of particles so that the particles don't come in direct contact with one another. One slide on tribological effect. I've more than mentioned it in here. Can be useful though if you've got a powder coating. Very often the object you want to coat is, which is a dry paint basically, the object you want to coat is given, say, a negative charge. The particles are given a positive charge in some way, and so they will attach to the surface. They'll go behind the surface as well. They'll fill in cavities, and then the system is put into a stove or an oven in order to melt it down to give you a nice white goods enameled finish that for an epoxy or an epoxy polyester type material, it gives you very good resistance. The last form of attraction that we will talk about, and this is a very significant one for small material, is bridges between particles that are formed in a number of ways. They can form from the drying of material out, the right-hand side shows salt crystal bridges between particles, or they can be bridged between particles from solid-solid diffusion. And obviously, this type of liquid type attraction, liquid bridges, a film of material there couldn't happen on most planetary surfaces or on the moon there, but that causes, from interfacial tension forces, a greater attraction actually than the van der Waals forces. So you can model, as you'll see at top right there, two spheres with the water or the fluid in between them, and you can make calculations of the forces dependent. Again, we have the size of the particles and the separation being key here. So if A is the radius and X the size of the particle, which is the usual nomenclature, then that A over X term is the one that's usually put on one axis, and the force on the vertical. Practical illustrations of this is a paper by Etzler and Udin in Kona, which is a Hosokawa publication from Japan, and I just illustrate that to show real-world particles and some of the issues that are faced when we try and make a pharmaceutical. This is insulin. This shows the various differences that occur with varying levels of humidity and greater attraction as you increase the humidity. So we take our material, we might make it in a dry winter, we ship it out to, say, Singapore or Hawaii with a big humidity, and we find that particles are stuck together very nicely, and that drying between surfaces, if they're reprocessed afterwards, can cause significant issues. We're not going to separate the particles out again by drying them. So this is taken from one of Rump's papers, I think, for the 62 one that I mentioned earlier. He was looking at forming agglomerates by solid bridging and then sintering, but cold sintering will occur with particles of small primary particle size, and by cold sintering I typically mean at room temperature. So two routes usually are forming those. Crystallizing salts I mentioned earlier, solid-solid diffusion there, and Jim Adair has shown a palladium black catalyst where the specific surface area reduced from 100 meters squared per gram to 2 meters squared per gram in about a quarter of an hour due to this particle-particle attraction and solid-solid diffusion. So here's one paper looking at spherical silicas here, rather like Ludox materials, and the arrows show the solid bridges between the particles, and of course they're not reversible at all. These are irreversible aggregates during the preparation, and you can't remove them other than by a technique called stress corrosion milling, which those bonds are areas of weakness. You can dissolve them. So with silica, you could dissolve them in concentrated alkali of high pH, but that takes care because you just want to dissolve the bonds and not the entire silica material. So any stress corrosion milling needs very careful feedback loops in order to do it. I've done that with copper powders, by the way, small copper powders with nitric acid, and what took 60 minutes with ultrasound could be accomplished in about 10 seconds with that particular form of dispersion. So solid-solid diffusion is actually used in diffusion bonded ceramic waveguides, something that I've got experience of many years ago at the Royal Signals and Radar establishment, where you could make high-powered CO2 lasers, because what you'd want is maybe a 20-micron hole in a foot of ceramic material, and you couldn't do that by drilling, so you'd have one surface in which that trench was carved at 20 microns. You'd have another surface. You'd have them very flat, and you just push them together. And in a ceramic material, the diffusion between the particles would cause the two layers to bond together. And these very flat surfaces, of course, but you'll see that's a route to producing something that would be otherwise very difficult, a 20-micron hole in a foot of ceramic. And the basis is fixed laws of diffusion. A few webinars ago this year, we did look at diffusion. Those solid-solid diffusivities of the order of 10 to the minus 10 to 10 to the minus 11 cm squared per second. Doesn't sound very much, but it implies that at 10 nanometers, you're going to get diffusion of atoms into atoms on the other side in 100 to 1,000 seconds or so. And the other implication is a lower limit to dry powder milling. Good paper by NIST authors, Zachariah and Carrier here. I'm looking at the bonding between particles and agglomerates of gas phase growth. So you produce your atomized aerosol of fine particles. When the particles interact or come in contact with one another or with surfaces, they form these, in certain cases, long chains, silica and carbon black being good examples of that. And this is why they find good use in rheological systems like toothpaste or whatever, in order to cause attractions, particle-particle attractions within long range, within solutions or whatever. But that form of head-to-tail linkage is quite common. And they examined the NIST authors, or modeled the diffusion of particles taking place. This is at 900 Kelvin. But the plot I'll show next This one here is the one that's, I think, crucial. If you look at the particle temperature along the horizontal axis, you've got a coalescence time for particles of various sizes, 30, 60, 120, 240, 480 atoms, which, you know, significant size. If you multiply up 480 atoms by the size of the atom, you'll see that coalescence time is in picoseconds. So if you back extrapolate to room temperature, you're still causing particles to coalesce if they're small in a very small amount of time. And I think, again, this for me is a very enlightening plot. In summary of that paper, so you've got your stable system in infinite dilution, perhaps atomized or in colloidal form. If you try and dry or sinter if you try to dry or filter such a material, the particles in contact with one another, and they form those closely bound aggregates on the right. So what we have in this situation with this solid bridging, this is a 2D representation of three spheres in contact with one another, the basis of a paper I wrote called, what was it called? Micron-sized nanomaterials or something like that, on that micron-sized nanoparticles. You'll see here that most of the surface area is accessible, but this behaves like a particle of much larger size because of those solid bridges. So those particles are not separated very easily other than by that stress corrosion milling that I mentioned earlier. The relation between the size of particles and the forces shows, of course, that diffusion and that attraction is significant in small particles. The inertial forces, micron is 1,000 times larger than a nanometer. Of course, those forces become insignificant at micron, 10, 20 microns or so. Paper by Kendall in here that I used to reference quite a lot. It's an 89 paper in here. He showed agglomerated or aggregated material in TiO2 of around a quarter of a micron, 300 nanometers in primary particle size, that there were aggregates in that system up to 100 microns or so, and that's what caused is processing issues, those fused particles. So a number of manufacturers now supply their titanium dioxide, barium titanate for ceramic materials in slurry form, because all of the work is done in creating those particles. It's all negated by drying the system and trying to have the convenience of shipping dry powders around. You simply can't redisperse them very easily to the starting size. So, you know, summary of what we've said before. Those attractive forces increase with increasing size, but it's a relation to the inertia forces that are key. That should actually read the other way around. Greater than 5 micron particles can be relatively easily separated. So as you run through a presentation, you see a couple of errors. Nanomaterials from primary size you can't separate. Stress corrosion milling, I will mention this, and you see the example I used earlier, the copper powders, 10 seconds as opposed to 60 minutes. Difficult to do in practice, needs careful pH change, needs careful concentrations. You can do a calculation. I've borrowed this slide from Jim Adair, but it comes from a paper from Biederhorn, who's still going strong in this paper from 1989. That's one of his classic papers, and I think he did have a paper from 1970 that was one. He's looked at a lot of adhesion between particles and separation of particles. There was a classic paper, I think, in one of the best 100 ceramic papers of the last century. I was going to say this century, but of course we're only 15 years into it. Your calculations show that if you've got two particles of silica adhering, that stress corrosion milling is feasible in a reasonable amount of time. And if you're looking at your ball mill, this is what happens when you get down to below a micron or so. Then your particles will recombine again after they've fractured. So the only way that you can get smaller than that by milling, of course, is wet milling with the appropriate additives. As soon as you've separated the particles, you'll cover them either with a polymeric layer that will cause steric repulsion between particles, so the particles can't go in contact, or with something like a phosphate that absorbs onto the surface, and from charge stabilization, that sometimes is called electrostatic stabilization, that keeps the particles apart. But in the dry, you can't do that, and the rate of breakage and the rate of recombination becomes closer, so you get a state of equilibrium there. Plus, the very small particles will flex and not actually bend when energy is applied. So crude back-of-envelope calculation will give you about a micron or half a micron or so for the lower limit of dry milling. So there's another quote which I could have used as my obligatory opening quotation. A good quote from Jim Adair here. If the particles are agglomerated and submicron, it may be impossible to adequately disperse the particles. The energy barrier to redispersion is greater if the particles have been dried. Therefore, the primary particles must remain dispersed in water. So drying your gold colloids is not a good idea. And we're just finishing with a couple of other quotes that I like. I use this in my micron-sized nanomaterials paper. This is Eric Drexler's quote of the micron scale is volumetrically 1 billion times larger than the nanometer scale. Confusing microtechnology with molecular technology is like confusing an elephant with a ladybug. Now, of course, I would examine that type of quotation very carefully. And if you do your ladybug and do a hard search, I had to weigh one, in fact, to find it was about 35 milligrams one summer day. And this is a cow elephant, and that's not bull elephant there. About 3.5 tons, 3,500 kilograms. You'll see that that ratio is about 1 times 10 to the 8. So Drexler's 1 times 10 to the 9 is out by an order of magnitude, but it just shows you the difference that we don't intuitively think. We transfer our thoughts at micron and larger down to the nanoscale, and it really doesn't work. So a few references in here to books on the gecko, to the classic text on intermolecular and surface forces with the applications to colloidal and biological systems. A good book on particle-particle adhesion in pharmaceutical powder handling by a lecturer at Imperial College there. Hans Rumpf, anything by him is good. Anything by Jim Adair I would recommend as well. Anything that Kellar Autumn or Kelly Miller is involved in, look at those carefully. So I'd like to thank you, but don't forget that if any of you speak Korean out there, that if you've got that form of gecko, it's actually the same vocalization as dog nose in Korean, and Cu, which is the chemical symbol for copper. So I will hopefully see you at the next webinar, and back to Craig in the UK studio.
Hi, Alan. Great presentation. Thanks for that. As I say, we'll just open the session now for questions and answers. If you can use the Q&A panel, type any questions, that would be great. Obviously, if you do have a private question, we can take those via email or offline. But if it's okay with you, Alan, we got a question that came in a few minutes ago.
Okay, fire away.
Have you used contact angle measurements of powders to characterize adhesive/cohesive forces?
Personally, I haven't, but I've seen references to that in the literature, the drop pendant method and other ways where the contact angle gives you an idea of whether a particle will adhere or not to a surface. Yes, so if you read that text by Israel Akveli, you'll see that those forces and that system explained quite well. Yes, so I'd like to fit that in a further presentation. But great question, and thank you for that.
Thanks, Alan. I've got a question here from John. How was the SSA measured during stress corrosion milling?
SSA is not normally measured during stress corrosion milling. It's normally done in the wet format and with a feedback loop. There's a patent by Jim Adair in this area that I can refer you to. So maybe that's a question we can deal with offline, and I can send you reference to that patent. But basically, he's following the stress corrosion milling by looking at the particle size of the system as it falls. So that will go through either a DLS or a particle size analyzer. You can measure the fall in the system or the rise in the specific surface area by that particle size distribution in the wet. In the dry, then of course it's classical BET specific surface area that can be used in order to do that single point in order to show that fall from say 150 meters squared to 2 meters squared per gram in the dry can be shown. But in the stress corrosion milling, which is a wet process, then you've got to monitor indirectly by the size distribution. Another great question. Thank you.
I've got another question, Alan. Is the limitation of ball milling also applied to polymers?
In terms of if it's dry, if it's a dry-based system, absolutely, yep. Those van der Waals and probably the solid-solid diffusions will probably be even more mobility in polymeric systems than in more solid systems. So I would have thought milling, other than in things maybe like liquid nitrogen, brings it down, but you've still got, even at liquid nitrogen temperatures, those van der Waals attractive forces occurring, so that's still going to provide that limitation. So if you're trying to make a nanoparticle by dry milling, I would think it's going to be a pretty hard task to do.
Okay, thanks, Alan. I've got another question here. So thanks for the great presentation. But when it occurs that the product is agglomerated during equipment measure, how do you measure the particle?
I'm not sure I fully understand the question, but I'll plunge into that. If you've got a agglomerated material, then you're measuring the size of the agglomerates and not the primary size. So if we go back to the slides that showed that solid-solid bridging, then the difference, for example, between a BET surface area, most of that surface area may be accessible, and the size you get from, say, a light scattering technique, the ratio between those is going to give you an indication of the degree of agglomeration in a system. Agglomerates can be separated by ultrasound as well. So if you're doing either a pressure size titration or looking at the effect of ultrasound in the wet, then your material at low energies is going to represent the agglomerated form. The material at higher energies, i.e. with ultrasound or higher differential pressures, is going to relate to a dispersed material. So the relation between the material as is with no energy input and that with increasing or high energy inputs is going to give you a measure of the agglomerates in the system. But many particle size techniques are going to be measuring agglomerate size. You have to be aware of that, anything from sedimentation to sieves light scattering. If that particles system isn't dispersed, then of course you'll be measuring agglomerate and aggregate size. But as I say, Jim Adair and Paul Bowen over in Switzerland, they look at the ratio between the particle size from a specific surface area. So specific surface area is 6 over D32, where D32 is the Salter-mean diameter. You relate that to a size, an agglomerated size, maybe by light scattering, and the ratio between the two gives you some measure of an agglomeration factor in the system. So yeah, good question again, and agglomerates are an issue in a lot of areas, from ceramics to paints, coatings, and whatever.
I've got one more question in from Stephen. May be able to take this offline, but Stephen wonders if you can direct to any papers concerning electrostatics and dry powders.
Yeah, I look at that reference list in there. The issue, of course, with electrostatic forces is that they can provide and do provide attraction, but the magnitude of them will change, and of course you can eliminate them. So if you get one of those nice magic radioactive ones that we used to use many years ago, and I think they were discarded on landfills, which is why I think they became banned, but you could get a nice little wand that if you created electrostatic forces by unwinding some tape, and I'll use that trade name sellotape, then that sellotape, when you unwind its huge static forces would attract to a wall. But if you took that tape, hung it vertically, and waved the magic ionizing radiation on it, it would hold down really limp like a piece of string with all the charges dissipated. So I think electrostatic charges, I'm not so familiar with them that they're able to, that I feel I'm able to control them, but they are used in many industries, and as I say, the one I relate to is the powder coatings one, where you coat a surface. But if you look at our dry powder feeders, it's another reason why you have to ground or earth the system very well, because you build up significant static charge from some materials, like polymeric materials like PTFE will build up huge amounts of charge and create adhesion. But there are routes for dissipating that charge if you wish. There are also routes for making that charge useful. So I guess it's a little bit like zeta potential in that way. You may wish to cause aggregation or agglomeration in a system by modifying the zeta potential. You may want to keep particles apart and stable by modification. So electrostatic charges do bear resemblance to zeta potential issues. So again, another good question. I'd like to, as Craig says, explore that offline as well.
Yeah, thanks, Alan. I'm just aware we are at the end of our sort of scheduled time for this session now. But if we can stay on the line if there are any more questions. But just to remind you, if you do want a copy of today's slides, you can use the file save as. And I know a couple of you did struggle to log in at the start. If you did miss the first few minutes, don't worry, this session is recorded, and we will send out a link to the recorded version early next week. And it's really great to see so many of you join today. So thank you so much for your attendance and for your attention. And I think that concludes the questions for the moment, Alan. So,
okay, well, thank you for hosting, Craig, and I wish everybody a great day, and I hope summer is coming back.
It's fairly foggy in the UK today, so.
It always is.
Yeah. Flights cancelled due to fog, so be careful if you're travelling to the UK.
Continent isolated.
Oh, sorry, Alan, we just got one last question come in. Is there any way to categorize the adhesive forces over a coating?
I mean, characterize is a tough word in that. I mean, you can look at various simple experiments as I showed earlier, but I tried here to deal with forces that related to in effect, smaller systems as we decrease particle size into the nano region. So I was steering away from the classic chemical and other glue-like type things. Let me have a think about that, but send me an email separately, and I'll have a think if I've got some additional thoughts I can add to that great question.
Yeah, actually, Alan just sent up an update today. He was referring to the forces between the coat and the support, but certainly we can answer that via email.
Yeah. Well, again, look at those simple experiments that were done by Kelsey and Kelly Miller at CSM. I'm sure, or an atomic force microscope would do that as well, but obviously that's more expenditure.
Okay, great. Yeah, any more questions, please do get in touch via email. I will leave the session open for a few minutes in case anyone does want to download the presentation. But yeah, thanks again, Alan.
Thank you again, Craig. Thank you especially to all our listeners and viewers today, and very much appreciated your time. Area of great interest to me, but I will now log out. So anything, please, you'll see the host and presenter emails up there. We're happy to try and deal with any questions that you have. But thank you all again. Goodbye.